This is going to be a tutorial on how to reduce data from Meerkat clusters of galaxies observations. In this particular reduction script, we're going to have a look at the bullet cluster. In Meerkat land, the bullet cluster has radio emission much like this, where you have obviously a diffuse component, but we have some background or compact objects shining through the cluster, and we have some very bright, relatively compact but not precisely compact areas, which are probably shock fronts, shocked regions or shock fronts, and we'd like to try and kind of separate out the shocked front regions from the global diffuse area in the middle of the thing. We'll come back and look at the observation over here in a few minutes. Anyway, as is the case for the Abel South observation, we have to use a .csv file because some of our data processing scripts are based largely on searching for giant radio galaxies together with Heinz Andernacht, and then we could have a list of, say, quite a number of different radio galaxies in this CSV file telling us what to look for and where they are. We don't want to have more than one observation in a CSV file for a cluster, and all the basic, we need to just have this frequency value in gigahertz, name of the object we're looking at, the RA and the DEC, and then this parameter here is a value used just for searching for radio galaxies. But next thing we have is a redshift 0.296 and minus 0.8, which we can use for cosmological data processing, etc. And so we want to execute the example script full, again, like we did with the Abel South thing. And as you see, there's going to be one extra operation here called separate masks, which we'll explain to in a little bit. So first we do the morphological processing. Now in this case here, this time we're just going to say, okay, the mask is fine. We're happy with it because as we're going to see, we're going to actually get rid of this guy completely in the next step. So we'll just turn it off. Now what we want to do now is, because when we do in-painting, the in-painting with using Navier-Stokes values takes emission from the surround, uses masks areas and fills in the masked areas using interpolated data from the surroundings. Now, in the case of this big ridge here, on one side, when we look back at the original image, we can see, let's just bring that back up again. We can see that this area here is kind of connected to the diffuse stuff on this side, but over here, there's absolutely nothing. So the in-painting, if we do it just without separating out the mask, etc., it's going to give a weird in-painting stuff on this area, because we can sort of fill in something from the right-hand side, but we can't fill in anything from the left side, so it's just going to be a weird mess. So what we're now going to do instead is, we know we don't want to in-paint in this thing, so we want to click on this guy this time, and that will actually remove that mask feature. And so when we did in-painting, we can see that basically nothing is being filled in here, except there's kind of a little boundary because of the left over from the fact that the mask was set to a threshold value of 9. So unlike in previous examples with this, we now can sort of say we have potentially a purely a cluster, diffuse cluster image, which we can now use to get the flux density. And go away and it'll figure that out. Then we actually convolve that image by a factor of 2 in case convolution shows that the flux density is increased because we're sort of smoothing a larger area, etc. Can select that and compute it again. And actually, if you look at the results from the parameter fitting there with the thing, that the flux density is actually not increased very much, so I think actually convolution is not pulling up a lot of extended features. Then finally, we can actually now compute a proper flux density of this object and some of these other surrounding little objects. Let's see, just do here. And you remember that I said that, let's just process that. And let's see. If we look at the parameters for that source cluster, first again, we as we do with the Able 2256, 22 Able South 1063 thing, we sort of have a global polygon, which in this case isn't very meaningful. And then we see a whole sequence below it of extended features, actually, all of them, and gives us a separate analysis of each of the extended features completely. So you can go and use that for what you want. For the individual observations of the diffuse and point clusters, there isn't too much difference. I might add, by the way, let's just look at when we go down and we want to get, since we've in-painted some of the areas, when we want to compute the flux densities of point sources, we have to still make sure that the flux densities in the original images did not sort of add in extra stuff because of in-painting, so that there's an image math thing here where you subtract off the essentially you subtract off image data where we've in order to, we want to subtract off the masked flux density, the actual bullet cluster values of the masked image data from. I'm probably confusing myself here, but we have to sort of subtract off a masked component of the flux density to make sure that total flux density at all locations sums to the what's the equivalent of the in-painted areas plus the original data, so we don't sort of end up adding extra flux density in the image. I'm probably confusing myself a bit on this. Anyway, that's about all we want to say, I think.